Hello students, welcome back to class 12 mathematics. Let me start with a quick thought experiment. Have you ever tried predicting how fast your phone battery drains when you keep Instagram open? Or how quickly money doubles in a savings account? Both these situations are modeled by equations that are first order and first degree differential equations. Now, mathematically, the general form looks like dy by dx equals f of x comma y. Here, dy by dx is the first derivative of y with respect to x, and it appears in the first power only. These equations are everywhere, from modeling population growth to predicting chemical reactions or even financial interest. But here's the challenge. Depending on the type of equation, we need to use different solving techniques. In fact, there are three superstar methods: separation of variables, homogeneous substitution, and linear equations with integrating factor. Let's go step by step. First up, the method of separation of variables. Imagine you're trying to untangle two different headphone wires. You separate them, deal with each one independently, and finally solve the mess. That's exactly what we do here. If the differential equation is such that f of x comma y can be expressed as g of x times h of y, then we can separate the variables. We rewrite it as 1 by h of y dy equals g of x dx. Now integrate both sides. So we have integral of 1 by h of y with respect to y equals integral of g of x with respect to x plus constant c. This gives us an implicit solution. H of y equals g of x plus constant. That's the magic of variable separation. Always check first if you can split the x part and the y part. If yes, life becomes very easy. Let's put this into action. Suppose our differential equation is dy by dx equals bracket x plus 1 bracket divided by bracket 2 minus y bracket with y not equal to 2. Step 1. Rearrange. Multiply both sides by 2 minus y and by dx. That gives bracket 2 minus y bracket dy equals bracket x plus 1 bracket dx. Step 2. Integrate both sides. The left side integrates to y minus y squared by 2. The right side integrates to x squared by 2 plus x plus constant c. Step 3. Rearrange into a neater form. X squared plus y squared plus 2x minus 4y plus c equals 0. This is our family of solutions, and interestingly, it represents conic sections. So, a simple looking first order, first degree differential equation actually gives us circles or parabolas depending on the constant. Next comes homogeneous differential equations. And no, it's not about milk or mixtures, it's about symmetry. A differential equation dy by dx equals f of x comma y is homogeneous if replacing x with lambda x and y with lambda y leaves the function unchanged. In simpler words, if the ratio y by x is what really matters, the general form becomes dy by dx equals g of y by x. Now we use a smart substitution. Y equals vx, which means dy by dx equals v plus x dv by dx. This substitution transforms the equation into a separable form in terms of v and x. Then, it's business as usual. Separate, integrate, and get your solution. So, homogeneous equations are like puzzles that want you to use the hidden clue, y divided by x. Let's practice. Consider the equation. Bracket x minus y bracket into dy by dx equals x plus 2y. Check homogeneity. The right hand side becomes bracket x plus 2y bracket divided by bracket x minus y bracket, which depends only on the ratio y by x. Perfect. It's homogeneous. Now substitute y equals vx. Then dy by dx becomes v plus x dv by dx. Substituting into the equation transforms it into a separable form involving v and x. After integrating, we get the implicit solution curve. Notice the pattern? Homogeneous substitution reduces complicated-looking equations into manageable, separable ones. Now let's meet the superstar of this chapter, linear differential equations. The standard form is dy by dx plus p of x into y equals q of x. Here, p of x and q of x are functions of x only. The secret weapon for solving linear equations is the integrating factor, often called IF. It is defined as exponential of integral p of x dx. Once we multiply the entire equation by this integrating factor, the left-hand side magically becomes the derivative of a product. D by dx of bracket y times if bracket close equals q of x times if. Then we integrate both sides. The solution is y times if equals integral of q of x times if with respect to x plus constant c divide through by if to get y done. This is the method that works for every linear first-order differential equation. No exceptions. Let's cement this with an example. Solve dy by dx minus y equals cosine x step 1. Compare with standard form. Here, p of x equals minus 1. Q of x equals cosine x step 2. Find the integrating factor. That's exponential of integral of minus 1 dx, which equals exponential of minus x or e to the power minus x, step 3. Multiply the whole equation by if. We get d by dx of bracket y e to the power minus x bracket equals e to the power minus x times cosine x, step 4. Integrate both sides. The right-hand side gives half of bracket sine x minus cosine x bracket e to the power minus x plus constant c. Finally, divide through by e to the power minus x to isolate y. The result is y equals 1/2 bracket sine x minus cosine x bracket plus c e to the power x. That's the complete solution, general family plus arbitrary constant. Let's wrap it up. Today we explored 3 powerful methods for solving first-order, first-degree differential equations. First, separation of variables. Split the x part and the y part, integrate, and you're done. Second, homogeneous equations. Check for symmetry, substitute y equals vx, and solve as a separable case. Third, linear equations. Bring in the integrating factor, convert to a product derivative, and integrate. So the big picture is this: every first-order, first-degree differential equation falls into one of these categories, and each method gives us a neat way to solve it. And that's the foundation of solving real-world problems with differential equations, from population growth to circuits to finance. In the next video, we'll explore applications of differential equations and see how math literally models life. See you there.